Right, Assalamu alaikum and hello everyone. So in this session, we're going to look at partial differential equation and the explicit. So if you remember from previous class, we have looked at parabolic, hyperbolic, and elliptic partial differential equation. So normally what we're going to look at is we want to predict the temperature at certain point under different time. So we can use the general heat equation. So for example, this is general heat equation for three-dimensional. And since our scope is only focused on x direction, one-dimensional, so the equation would be up until here, which is given as this one. And so from the one-dimensional heat equation, we can use what we have learned in chapter 5, numerical differentiation. So this is for first order differentiation. This is second order. First order is against time. Second order is temperature against distance x. So basically we can replace with this equation, replace back into here, replace back into here, and we can get this is what we call as explicit finite equation. Yeah, and from this explicit finite equation, we can get the computational molecule. And yeah, basically we can predict any temperature at T plus 1 by using the values at T. Right, so let's look on how we're going to solve it. So from general heat equation, and this is a 3-point central difference, this is 2-point forward. So we replace this in the equation. So delta T over dt can be written as T x T plus 1 minus T x T over delta T. Okay, I'll write as dt. So this represented by this is equals to K, which is the thermal diffusivity, multiply with delta squared temperature against delta x squared, where we can use 3-point central difference. Okay, so T x plus 1 T minus 2 T x T plus T x minus 1 T over delta x squared. So where do I get this? I get this from here, okay, by substituting second order and first order into the general heat equations. So next, we just want the terms, we don't want any denominator on the terms of txt. So this we bring to the right, it will be k delta t. And this one, if we factor it out, we got k delta t over delta x squared. So this is equals to bring this to the right, we got delta t over delta x squared. Okay, so k delta t delta x squared multiply with dot terms, so which is this one. Okay, so maybe I just put a bracket, that will be more clearer. And all right, so if you look here on the left hand side, we've got the terms of t plus 1 and t, and on the right hand side, okay, the second coordinate, which is t, is only t, t, and t. So what we're going to do is that we're going to organize so that the left-hand side will just only contain t plus 1, and the right-hand side will contain t only. So what we do is that we'll bring this to the right-hand side. Yeah. So t x t plus 1 is equals to this. Okay. Yellow it, multiply with this. I will also yellow it. Okay. Since this we bring to the right, okay, it will become plus dxt. All right. So please remember that you can't simply solve negative 2txt plus this. Okay, it will not end up negative 2 plus 1. It will not be negative 1 because all of this term you need to multiply with k delta t over delta x squared. So once you have multiplied in here, then you can plus with the txt, right? So this is what we call as the explicit finite difference equation. So generally, when you have partial differential equation problems, for example, explicit problems, you need to first develop the explicit finite difference equation. So this is the explicit finite difference equation. So once you have developed this, you can come out with the computational molecule, okay, whereby basically this is what the computational molecule is. Okay, so this is the explicit finite difference equation. So this is at time equals to t. This is at t plus 1, and this is at t plus 2. So from here, okay, the temperature at this point, okay, txt plus 1. If this is x, this is the next point will be x plus 1. The point before will be x minus 1. So the temperature at x, where the time is t plus 1, is equals to the multiplication of this constant multiply with this, okay, tx plus 1t minus 2 this plus this and plus this, right? It's quite hard to obtain yet, but basically from the explicit finite equation, you can get this computational molecule. Okay, so this is what we call as computational molecule, whereby it helps us to visualize, okay, the temperature. If we want to find the temperature at one point, we can use the point before, right? And once we have developed the computational molecule, we can find the temperature at each point by drawing the temperature difference rate. So what is temperature difference rate? So basically, this is the temperature difference rate. All right, so let's try to solve example 9-1. Right? So when we look at this example, okay, A 40 millimeter straight steel bar is heated in 8 seconds at its ends. So meaning that both ends, okay, both ends was heated for 8 seconds, point A and point E. The initial temperatures are shown. So basically this is the initial temperature when T is equals to 0. For example, point A is 25, point B is 30, point C is 50, point D 35, and point E is 25. The heating process is going up slowly as illustrated. So it was illustrated in here. So meaning that at 0 second, the temperature at point A is 25. At 4 seconds, the temperature at point A is 28. And at 8 seconds, the temperature at point A is 30. So this shows that it was heated, okay, for 8 seconds with delta T. If you look here, delta T, the difference between one time to another time is 4, where 4 minus 0 is 4, or 8 minus 0, 8 minus 4 is also 4. So delta T is 4. So on point E, at time equals to 0, the temperature is 25. And as it was heated for 4 seconds, okay, the temperature at point E is 30. And as it prolongs 8 seconds, the temperature at point E is 35 degrees Celsius. So from 25, increase to 30, and increase to 35 for point E. Thermal diffusivity is equal to 10 millimeters squared over second. So if you remember on the general heat equation, we've got this K, okay? So this is what we call as thermal diffusivity, given as 10 millimeters squared per second. So the question asks us to propose an explicit finite difference equation to find the transient temperature of the bar at T equals to 8. So what does it mean by transient temperature? Means that it wants us to predict the temperature of point A, B, C, D, and E when it is at 4 seconds and at 8 seconds. So that is what it means by transient. Okay, transient is related to time, and calculate all points at 8 seconds after the heating. So again, it wants us to calculate point A, B, C, D, E at 4 and 8 seconds. So how are we going to do that? Okay, so this is example -1. So first, remember that we need to develop the explicit finite difference equation. So how do we develop that? Okay, we can develop it from this general heat equation. Okay, so this is general heat equations. So replace the first order differentiation against time with this. So we get T x T plus 1 minus T x T over delta T. And this is equals to K. So K multiply with the second order T against distance. So T x plus 1 T minus 2T x T plus T x minus 1 T over delta x squared. Okay. So next, what do we do? Bring this to here, bring this to the right. So we'll just left out with this. So this will become delta T over squared multiply with this term. So since we have the value of thermal diffusivity, which is our K, and we know that delta T is 4, so we can get this value. However, at the moment, we don't have delta X squared. So in order for us to find this yellow field value, we need to find what is delta X. If you read the question carefully, it mentioned that AE is equals to 40 millimeters. So if you can see, it is divided into 4 divisions, which is AB, BC, CD, and DE. And this is distributed equally, whereby distance of AB is equals to BC, equals to CD, and equals to DE. So since from here to here is 40, if this is 0, this will be 10, 20, 30, and 40. So you know that the distance between A to B is 10, B to C is 10, C to D is 10, and D to E is 10. Or one way for you to find, if you still remember, H is equals to Xn minus X naught over number of division n. So our Xn here, E, is 40, X naught is 0, and n is number of division, which is 1, 2, 3, 4. So 40 minus 0 over 4, you get equals to 10. So meaning that our delta X is equals to 10. Okay, dx is equals to 10. So replace all the values that we have known. Okay, so K is 10. Delta T is given as 4 seconds. And delta X squared is 10 to the power of 2. Okay, so this is actually equals to, wait, let me calculate, equals to 10 times. So 40 over 100, you get 0.4. So this is equivalent to 0.4. So 0.4 is K delta T delta X squared. Okay, put it as yellow so that you can see. And we've got this. Okay. So if I expand this, okay, because basically here we've got bracket here, meaning that everything needs to be multiplied with 0.4. So the equation will become 0.4 so 0.4 Tx plus 1 T minus 2 times 0.4, you get 0.8 minus 0.8 plus 0.4 Tx minus 1T. So what I did just now is that I'll just expand this, multiply this multiply with this, and this multiply with this. So remember that previously we said that we want only T plus 1 for this term on the left hand side. So we bring these to the right hand side. Okay, So since negative txt we bring to the right will become positive, okay? So this plus this, you can simplify negative 0.8 txt plus 1 txt become 0.2 txt. So our explicit finite difference equation would become negative 0.8 plus 1 is plus 0.2, and don't have this anymore. So maybe I'll just leave some space so that you can see it clearly. So this is our explicit finite difference equation. So if we refer to the computational molecule, okay, so this is computational molecule, okay, at state t plus 2, t plus 1, and initial state t. So txt plus 1 is equals to 0.4 tx plus 1t. So let's say this is top, front, middle, back. So to get the top value is actually 0.4 front plus 0.2 middle. Okay, 0.2 middle is txt plus 0.4 back. Okay, so we can predict the value here. So if we relate with our question here, okay, we got A, B, C, D, and E. So let's say all right, we've got this bar. We've got point A, B, C, D, and E. So what we want is that we want to predict the temperature at 4 and at 8 seconds. So if this is T, this is T plus 1, and this is T plus 2. Okay, so our grid, okay, our temperature grid, okay, basically would have, example, this is at T, okay, up is T plus 1, and this is T plus 2, whereby T plus 2 is actually 8 seconds, T plus 1 is 4 seconds, and T is actually at 0 seconds. Yeah, 8 seconds, 4 seconds, and 0 seconds. So what we want is that we want to predict the temperature at point A, B, C, D, and E. So let's just imagine this is point A. Okay, maybe I use yellow color. So this is point A. This is point B. Okay, so I'll use green color. And point C. And D. And point E. Well, I didn't use it, put in with purple. So this is what we call as finite difference grid, yeah, temperature difference grid, whereby this represent point A, point B, point C, point D, and point E. Okay, and at different time, for example, this is at t equals to 0, this is t equals to 4 or t plus 1, and this is at t equals to 8, which is t plus 2. So we can write it as T1, T2, T3, T4, 5, T6, T7, T8, T9, T10, and this is T11, T12, T13, T14, T15. Okay, I just don't like this purple color, so maybe I'll replace it with gray. Yeah. Okay. So at initial condition, we already know the T1, T2, T3, T4, and T5, whereby T1, T2, T3, T4, and T5 is actually T1 corresponds to point A when T equals to 0. T2 is the temperature at point B when time is 0. C, D, and E at time equals to 0. So here, temperature is 25, 30, 50, 35, and 25. Now, when t equals to 4 seconds or at t plus 1, actually, we already know what is the value of point A and point E, but we don't know the value at point T7, T8, and T9. So if you refer back to your question, it already said point A at 4 seconds is actually 28 degrees Celsius, and point E at 4 seconds is 30 degrees Celsius. So it's 28 and 30. So meaning that since this is point A at 4 seconds, this is 28 degrees Celsius and this is 30 degrees Celsius. 28, 30, 30, 35. And T11, which corresponds to point A at 8 seconds, is 30 degrees Celsius and 35. T15, which is point E at 8 seconds, is 35 degrees Celsius. So this value is actually the temperature. So by using our explicit finite difference equation, okay, we can predict T7, T8, T9, 12, 13, 14 by using this. So if you remember the computational module, which is this one, okay. So basically, if let's say this is our X, so the next point at C would become X plus 1. And the point before X is X minus 1. So to get the temperature at X and time is T plus 1. So T7 equals to 0.4 Tx plus 1T. So first you look at the X coordinate. If this is X, so this is X plus 1. And the Y coordinate is at T. So here is T plus 1. This region is T plus 1. This region is T plus 2. So this is the region where it's only T. So so for T7 is actually 0.4 T3 plus 0.2 T2 plus 0.4 T1. So 0.4 T3 plus 0.2 T2 plus 0.4 T1. Okay. So you place, basically what you need to do once you got this, you can put this in your calculator, whereby you can use 0.4 A plus 0.2 B plus 0.4 C. Put this in your calculator. So your A is corresponds to T3. Your B is correspond to T2, temperature at point 2, and C is correspond to T1. Since we already know what is T3, T3 is 50, T2 is 30, T1 is 25, just put in your calculator. So T7 is equals to this. So T7 equals to 36. So how do I get that? Because from our explicit finite difference equation, so T7 is actually 0.4 T3 plus 0.2 T2 plus 0.4 T1. So replace all the values of T3, T2, T1 in your calculator, you can get T7 equals to 36. So same thing, how do I get T8? So T8 is actually 0.4 T4 plus 0.2 T3 plus 0.4 T2. So T8 is 0.4 T4 plus 0.2 T3 plus 0.4 T2. Okay, replace the value. And the answer is 36. Okay, let's just check. So 36, 36. So we got it correctly. Okay. Once you get the value, just update in your temperature difference grid. And then how do we get T9? Same thing. T9 is actually 0.4 T5 plus 0.2 T4 plus 0.4 T3. So T9, 0.4 T5 T4. So it's 37, right? Just check. Yeah, T9 is 37. Okay. All right. So we already determined this point. So for the next time, which is T plus 2, okay, same thing. T12 is actually 0.4 T8 plus 0.2 T7 plus 0.4 T6. Okay, so T12 0.4, T12, 0.4, T8, T7, and T6. Okay, so since we use this value, so the answer is 33. Check back, 32.8. So if I change it into decimal point, actually we got 32.8 degrees Celsius. So update it in here, 32.8. Okay, so by using the similar approach, okay, I want you guys to finish up with T13 and T14. All right, so basically we have proposed an explicit finite difference equation. So this is the explicit finite difference equation. And we have also calculated all points at 8 seconds. So I have done up until here. Okay, so I didn't do this two yet, and I would like you guys to do it on your own. All right. Okay, just want to recap. Basically, when you get this kind of problem, first, we need to develop our explicit finite difference equations. So how do we develop this is from the general heat equation. Okay, we develop it. And then we replace the K delta T over delta X squared value, expand it, okay, and simplify it, you get your explicit finite difference equation. And then from here, you can draw this. This is what we call as computational Q that can visualize to us. So to find this value, it's actually 0.4 this plus 0.2 this plus 0.4 this. Okay. And draw the temperature difference grid. And from here, you can predict the temperature for all points. Right? So basically, if let's say previously we don't have this value. So from here, you know that in order for you to get the temperature value here, you need to have these three values. Since we don't have these two values yet, that's why we need to start from here. So to get here, we can use these three values. So that's why we start from 7, 8, 9, 12, 13, and 14. So that's all for today's session. Please complete up until T13 and T14. I'll see you again in next class. Thank you very much.